Hi students, today we are going to see about alloys and phase diagram. In our world, we can see engineering materials are categorized into four: metals, ceramics, polymers and composites. The most important engineering material is a metal. They have properties that satisfy a wider variety of design requirements. The manufacturing processes by which they are shaped into products have been developed and refined over many years. Why metals are important? It has high stiffness and strength. Also, this metal has toughness, good electrical conductivity, good thermal conductivity, and the cost wise, the metals are easily available at very competitive with other engineering materials. Starting form of metals used in manufacturing processes are cast metals, roughed metal, powdered metal. If we see cast metal, our starting form is a casting. Roughed metal, the metal has been worked or can be worked after the casting process is done. Powdered metals are starting form is very small powders for parts using powder metallurgical techniques. Classification of metals. If we see, ferrous and non-ferrous are the basic two types of metals. Ferrous having steel and cast iron are the types. Non-ferrous having other than the iron content are non-ferrous metals. For example, aluminium, magnesium, copper, nickel, titanium, zinc, lead, tin, molybdenum, tungsten, gold, silver, platinum and others. And we can see super alloys also. These super alloys are used for high quality based, high life expansion needed areas. We can use the super alloys. Metals and alloys. Some metals are important as pure element. For example, gold, silver and copper. Most engineering application requires the enhanced properties obtained by alloying. It is possible to increase strength, hardness and other properties compared to pure metals. If we see alloy is a mixture or compound of two or more elements, at least one of which is metallic. There are two major categories of alloys are there. One is solid solution, another one is intermetallic phases. Solid solution is a form where alloys one element is dissolved in another to form a single phase structure. This single phase having a homogeneity mass of material, such as metal in which the grains all have the same crystal lattice structures. Two forms of solid solution. If we see the picture A is representing substitutional solid solution. Here the atomic level of the elements are replaced by another metals. But in the image B, if we see intestinal solid solution, the atom of the metal in between the gap, another particles of the metal is added. It increases the hardness of the material. If we see the phase diagram, it always shows the graphical representation of phases of a metal alloy system. Phase diagram for an alloy system consisting of two elements at atmospheric pressure is called a binary phase diagram. This phase diagram has composition is plotted on horizontal axis and temperature on vertical axis. Any point in the diagram indicates the overall composition and the phases are phases present at the given temperature under equilibrium conditions. For example, if we see the phase diagram copper and nickel, from the left hand side copper is keep on adding up to 100. From the right hand side nickel is keep on reducing from 100 to 0. If we see copper is going to be start at the melting point of 1083 degree centigrade. If we see the nickel at 1455 degree centigrade, it starts from solid to liquid state. In between the phases, when the percentage of the copper and nickel is keep on added, the binary phase of the diagrams is going to be drastically changing. From the solid region, it creates a solidus layer. From the high melted temperature of the liquid solution, if we see, it creates a liquidus layer. In between the solidus and liquidus layer, liquid plus solid content are in a mixture of binary phase. In alloy system, solid solution alloy throughout either range of composition below the solidus. Non-intermediate solid phase in this alloy system. However, there is a mixture of phases solid plus liquid in the region bounded by the solidus and liquidus. Chemical compositions of the phases. The overall composition of the alloy is given by its position along the horizontal axis. However, the composition of liquid and solid phases are not the same. If we see eutectic alloy, the particular composition in an alloy system for which the solidus and liquidus are at same temperature. If we say eutectic alloy, the eutectic means easily melted in a Greek word. The eutectic temperature is always the lowest melting point for an alloy system. Ferrous metals. Based on iron, one of the oldest metals known by man is ferrous metal. Ferrous metal are divided into two major groups. One is steel, another one is cast iron. If we see ferrous, iron carbon phase diagram is a very good example for the iron content Fe. We are going to add from 0% to 6% of the carbon content in the iron carbon phases, we get different types of result. The phase at room temperature is alpha, called ferrite, it having the BCC structure. at 912 degrees centigrade, ferrite transforms to gamma called arsenide. This arsenide having FCC structure. This transforms at 1394 degrees centigrade to delta. This delta is again come back to FCC structure to BCC structure. Pure iron melts at 1539 degrees centigrade. Ferrite phase can dissolve only about 0.022% carbon at 723 degrees centigrade. Arsenide can dissolve up to about 2.1% carbon at 1130 degrees centigrade. The difference in solubility between alpha and gamma provides opportunities for strengthening by heat treatment. If we see the steel, iron carbon alloying contains from 0.02% to 2.1% of the carbon. In the iron carbon equilibrium diagram, cast iron having the 2.1% to 4% or 5% of the carbon content. Steel and cast iron can also contain other alloying elements besides carbon. Cementide in the iron carbon system. At room temperature, under equilibrium condition, iron carbon alloys forms a two-phase system at carbon levels even slightly above zero. The second phase is Fe3C, also known as cementide. Cementide, an intermediate phase, a metallic component of iron and carbon that is hard and brittle in nature. Eutectic composition of iron carbon system is 4.3% of the carbon content. Eutectoid composition of iron carbon system starts at 0.77% of the carbon content. Below 0.77% of the carbon content called hypoeutectoid steels. From 0.77 to 2.1% of the carbon content, we are saying hypereutectoid steels. Iron and steel products are having iron making from iron is reduced from its ore. Steel making iron is then refined to obtain desired purity and composition in alloying. From this video lecture, the phase diagram of the iron carbon structure is very well known. Thanks for listening.